Today we're going to be talking about decision trees. Decision trees are a very simple and intuitive model, and I'm going to start us off by giving an example of what a decision tree looks like, and then we'll sort of talk about them specifically and how to use them for machine learning problems, as well as how to create them. Okay, so let's start by, let's suppose you wake up one day and you decide you're going to go outside, and you're wondering, should I wear a jacket or not? And your decision might go something like the following. You might first check the temperature. And basically, if it's cold, then you'd consider taking a jacket. So let's say if it's below 15 degrees Celsius, then you would take a jacket. On the other hand, if it's above 15 degrees, then maybe you wouldn't. I guess we want these to be joined. Now, the thing is, if it's above 15 degrees, then maybe there's some cases you might need a jacket in case it's going to rain. So for example, what the next thing you would do is maybe see if it's cloudy or not. And if it's cloudy, question mark, then in this case, you would take a jacket. Otherwise, it's warm and there's no clouds or anything. Then in this case, maybe no jacket. So what you can see here is we made a very simple decision tree based on the day and the label, based on features of the day, and the label would be whether we should wear a jacket or not. So it'd be something like the following, where our feature vectors X are going to have pairs which are the temperature and whether it's cloudy. They're going to be two-dimensional feature vectors, and our labels are going to be they're either going to be wearing a jacket or no jacket. So yeah, this is a decision tree. And let me just remind you about some of the terminology that we're going to use when we're talking about trees. So this is a tree, as we've seen, I'm sure you've seen many times in computer science. It is a binary tree because each node has at most two children. We're not necessarily going to be, decision trees might not necessarily be just binary. They could have more children. But at least for today's lecture, we're just going to be drawing them binary. I'll remind you that these nodes at the bottom, which don't have any children, these are called leaves. So the leaves are this one, and this one right here. And this node right here at the top is the root. Okay, so that's the basic terminology we're going to need for decision trees. So you can see that if you have any sort of feature vector, you can follow it from starting from the top to figure out what you should classify it as a jacket or no jacket day. So yeah, it's very simple to start at the root and just check each feature one by one. So temperature, if it's greater than 15, then you check if it's cloudy or not. And then if it is, then you wear a jacket. Let's draw this a slightly different way, which is, which maybe you'll see how this is. Yeah, let's draw it like this. So what we'll do here is we're going to draw it as a 2D picture in the plane. So we'll just start by drawing this, and this will be the feature whether it's cloudy. And it's just going to be yes, and this will be no. And this will be the temperature. Let's say 15 degrees. I don't know, this is less than 15. Let's say, I don't know, it goes to minus 20 degrees. It go colder sometimes, and this is say like 40 degrees. I don't know. Okay, so this is a way of looking at points in if we have x vectors, which are in 2 dimensions, this is a way of visualizing what it looks like in 2 dimensions. And let's try to draw what the decision boundaries look like if we were trying to make this into a classifier. This is perhaps a bit closer to the pictures we've been drawing before. So it would look something like this, where I guess it's not exactly the same thing as before, but essentially it would, what this first does is it splits on temp, whether it's less than 15 or greater than 15. If it's less than 15, then things on the left are going to be, I guess let's do this in orange just to be consistent with what we've done before, would be jacket weather. So anything in here would be classified as a +1 in terms of wearing a jacket. And then as for the other half, well, we can see that it splits based on whether it's cloudy or not cloudy. So we're going to split here, kind of in the middle, and yeah, label things correspondingly. If it is cloudy, then that's jacket weather. In case it's gonna rain, and this one over here will be no jacket. Cool. So hopefully it's clear the sort of correspondence between this decision tree I drew here and this sort of classifier that we drew in the plane. So yeah, this is the basic idea behind decision trees. You're going to try to build one of these so that based on your training data, you're going to try to create one of these decision trees. So then when you get a new test point, you'll be able to figure out how to label it based on following these rules in this decision tree. So what are a few key points about decision trees? So some of the key things are, one plus is that these are very simple. They're simple because, yeah, I don't know, they're simple in a number of different ways. One is that anyone can use them. For example, if you show a decision tree like this, someone who has no knowledge of computer science or math should be able to figure out how to do it. They're very simple in that way. They're very easy to implement comparatively, compared to some of the other things, which are, for example, gradient descent, which can be a little bit tricky sometimes. You need to sort of tune various parameters, so this might be simpler in some cases. Another benefit is that it is interpretable. And this is a very important thing for certain applications. For example, often there's certain questions you can ask. For example, the use of machine learning in the use of machine learning in medical settings. In these types of settings, what if a machine learning algorithm tells you that you should operate or prescribe a certain sort of treatment for an illness, and you ask the machine learning algorithm why, and it can't tell you. So this is kind of a bit worrying because it can't really be as easily audited to see why it made the decision it did, and a doctor or an independent other person can't necessarily make the same decision, and they don't really know whether this is the right thing to do based on the reason that the machine learning algorithm gave. Whereas for a decision tree, it can be very nice because you can see something like, I'm sure there's certain things like based on their temperature and based on their symptoms, we had a decision tree, and then that's why we prescribed this sort of treatment. And that's interpretable, and a doctor can maybe see that and say, yeah, this is the right thing to do. So in some settings, interpretability is very important. I'll mention also that this is flexible. It's flexible in the sense that it can be used for either classification or regression. And this example that we had here is on classification because it's either jacket or no jacket. But I'll mention at one point, essentially, what would you do if you want to do regression instead? And it's honestly pretty simple, similar to all the other things. Instead of just getting to some sort of label at a leaf, it'll get to a prediction for a value, which will be, a continuous or real value. It's really pretty similar. Yeah. Another thing to mention is that, let's see, this is also going to be, let me mention that sometimes this is not great because there's some downsides of the type of algorithm. It's kind of a simple model, which isn't always great all the time. And something that it happens to do is it tends to overfit sometimes. There are ways of getting around this, but it literally tries to classify the training data as well as it can under these models. You can imagine, well, I said they're simple, you could imagine that there's a lot of different rules and it splits a lot, and it could tend to make up a really, really convoluted set of rules that would classify every training point correctly, but then it wouldn't do well on the test data. So if you're not careful, it can overfit very easily to your training data and give you a total nightmare of a tree. And we'll talk a bit about how you prune a tree towards the end of this lecture. And let me just give you, tell you what some sort of strengths and weaknesses of them. Some sort of strength is that they can handle nonlinear functions. But they might not be great at linear functions. And I'll show you some examples of each of these. So the reason why they can't handle linear ones, let's do that first. Well, the idea is we haven't really got to where these trees come from, but the essential way they work is by taking a variable and splitting it. So you're going to end up getting something, splitting it and splitting it again and splitting it again. So essentially your classifier that you're going to end up with looks something like these axis-aligned rectangles. And so if you're making classifiers only based on axis-aligned rectangles, then there's some cases which they just won't be able to do well. For example, let's suppose we have this space, and then we have, let's say some, what is it? Let's say we have some space down here where everything over here is a +1. So this is going to be labeled this way. And everything above is going to be labeled as like -1. So you can see right here immediately that this would be a great type of thing where an SVM or logistic regression or perceptron, even any of the algorithms we've studied so far, which are linearly based, could do great on this. But you can see this wouldn't really necessarily do well on a decision tree type algorithm, wouldn't really be doing too well on it, because if you, as I said, we're going to discuss a bit more why this happens, but it's really constrained if you do it the common or natural ways to generating some sort of axis aligned rectangles. So for example, instead you would get something which maybe looks like, okay, maybe it would try to split like this, get like this, and then maybe and then everything here would be correct, but now you've got something which is a mix of blue and orange. So maybe it would have to do something like this, and maybe it would have to subdivide these each. It would basically be trying to approximate this by a series of rectangles, which is not necessarily an easy thing to do if it's a linear function. So this is a vague example, but hopefully it makes sense that if we're only looking at axis-aligned rectangles, then it would be not great at solving things like this. On the other hand, let me give you an example. Let's go a little bit more about, I'll give an example of a nonlinear looking function that it is able to learn, and kind of how we would go about making the decision tree. I'm not going to be formally making the explaining the step-by-step of how it does it algorithmically, but I'll just kind of show you what an execution of a decision tree would look like. So yeah, this is a linear function it can't handle. Let's do a nonlinear function that it can handle. Okay, let's draw a new thing. So here is let's draw our data set, and first of all, I'm just putting some axes here. I'm just going to call these some arbitrary features. These are features, so like x is equal to a comma b. And this will range from, let's just pretend they're from 0 to 1. 0.5. Here, 0, 1. 0.5, let's say. And let's draw some points and say what it's going to look like. Bear with me for a sec while I draw a bit. All right, so here we go. Here's an example of a data set. And you can kind of see, maybe if you eyeball it personally, what the like right decision boundaries you might put here are. For example, maybe at the top left, you see there's a lot of ones there, and so everything here would be classified as a 1, and then things at the bottom right would be 1, so maybe you'd put a bounding box around that. But let's try to see a bit more precisely how an algorithm would go about building a decision tree for this function, and how we would come up with, how we would learn based on this. So let's start off nice and simple. Like, I'm not going to get into the details of how it makes these decisions right now. I'm just going to illustrate how we would build this, but we'll talk more in terms of how you might actually implement this and what sort of rules that you're going to follow. Okay, so the first thing we'd start with is just a trivial sort of classifier for the whole thing. Okay, so we have any point. If it's any point, then what is the way of classifying a point? Well, we see it looks like there's probably more minus signs than plus signs here. So if I just told you you have a point and is a majority of them are minus ones, then you would just label it -1. So here's the basic, most simple decision tree you can imagine. It's just a single node, and that node says if you get a point, classify it as -1. Done. Now, of course, this isn't great. So what we can instead do is we can somehow split it. Like, we're going to take this node here, which is just saying any point is classified as 1, and say that, hold on, take a look at the value of this first coordinate, a. You'll note that if this value a is large, then it's more likely to be a +1. And if this value a is small, then it's more likely to be a -1. So, okay, what we're going to do is we're going to split. So let's draw what it looks like here, what this split would look like in this decision tree, or in this sort of coordinate representation. Basically, would say something like this. This is a good way to split things. So this old decision tree would basically become the following. You would basically take a look at the value of a, and then based on the value of a, you'd make a decision. For example, if it's less than 0.5, then now you have a new node here, which is going to be labeled minus, because you can see when you're on this half, it's a majority minus. And on the other hand, if it's greater than or equal to 0.5, then here on this side, it'll be plus. Good. That's the first step we can do, but it turns out that within each of these, we can actually do even better. So let's ignore the left side for now, but take a look at the right side. The right side, notice how nicely it can split in the middle here. For example, if you just draw a line here horizontally, then in fact, this is another way to split, which would give us a very good prediction on the bottom half. Like what we would do here is if anything falls in the right half, because the majority pluses, then anything in the space would be a plus. But we can see that doesn't really represent the space at the top right here very well. Therefore, the right thing to do is going to be to split. And now what we can do here is if we're in the bottom right, then we can predict +1. And if we're in the top right, we can predict -1. Like I said, this is another split. And what we're going to do is we're going to split this node right here. So that corresponds to this. And this would split into two things based on the value of b now. That splits into two things. So this is about 0.5 as well. So if it's less than 0.5 versus greater than or equal to 0.5. And we can see that in the less than 0.5 space, it goes to plus. And in the greater than 0.5 space, it goes to minus. And you can see this is a pretty good classifier, I'd say, for both of these spaces. That's probably as good as it's going to get for this picture. On the other hand, on the left-hand side, you can see that you can similarly split it with a different value of b. So you can see here that if you kind of draw the line up here, then maybe that's a good way to split, and everything down here can be classified as a -1, and everything up here can be classified as a +1. So here we have another split on b, and now this time it's not going to be 0.5 as we've done everywhere else, but say less than 0.75. And here it'll be, say, greater than 0.75. And we will put a plus here and a minus here. Again, and the reason is because we basically look at our training data and pick the majority within that cell of this space here. So yeah, and that's probably what we want as our final classifier. You could try to make it more fine-grained in terms of like maybe carving out some spaces which contain each of these, but that might overfit, to be honest. So this is probably as good as it's going to get. So let me just point out that this is a rather non-linear looking function, which a decision tree could handle quite well. So, okay, that's just an intuitive look about how to how a decision tree might be made by looking at the data. And the kind of intuition is that we're going to start with a very simple decision tree, but we're going to keep splitting the leaves of this decision tree again and again, based on what type of splits would make the resulting leaves look very homogeneous, like all one type. So for example, when we split the beginning, we saw that we could split it in a way that would have a lot of minuses on the left and a lot of pluses on the right. And so we did splits like that until it seemed like things were fairly homogeneous in each of the final cells. So intuitively, hopefully that makes sense. Yeah, and we're going to get into how to actually build a tree in a second. The first thing in terms of, okay, we've built this tree here. Let me just tell you how to classify, because I've already told you this a bit before, but it's very simple. So yeah, let me just say prediction. And all you have to do for prediction is walk down the tree. And use Leaf's prediction. So just to give you an example, let's suppose we had the point which was, say, I don't know, 0.3, 0.7. So how would we do this? Well, we would just take this and walk down the tree. So the first coordinate is 0.3. And so we say that, okay, it's in this area. A is less than 0.5. So we go here. And then for the other one, we check if B is greater than or less than 0.75. It's less than 0.75, so we end up here. And so it would be classified as a minus. Now, how does this work? We essentially, like, where would this point be? It's going to be right about here. And so, yeah, naturally, you can see if you just look at this, this is going to be a minus. Cool. So let's see, what is next? So yeah, that's how we do prediction using this. The next thing is the sort of tougher part. We have to talk about how to actually build a tree. And that's what most of the lecture is going to be focused on. So let's talk about how to build a tree. And the main idea is just to start, like I said, we start with a node, and then we're going to keep splitting it and splitting it until we have a whole tree that looks nice like this. So yeah, let's say building a tree. So how do we do it? So again, if the simplest possible tree we could have is just one node. And all we would do in this one node is we would start by predicting the majority class. Like, recall this is what I just had, where you have just a minus. And then for that case, you would predict the majority label. Yeah, this is easy, a very simple classifier, but it's not very useful. And so from here, we're going to build a tree recursively. By every time we have a leaf, we're going to split it. And then we're going to we're going to split it into two subtrees. So, okay, let's see how we split it. So let me just write this. Start with, I guess, one node, recursively split. And what we're going to do is we are going to choose a variable to threshold on. Yeah, this is roughly how it's going to go. We are going, what is a split function going to look like? It's going to take in a leaf. And what it's going to do when you have this leaf is you're going to choose a variable plus a threshold. And then you're going to create two leaves with a partition of points. And how do you do this? well, this is basically what we did here, where each time you pick a feature and then we picked how to split it. So I just said we do it. We haven't really talked about how, so we'll talk about that in a sec. But essentially, you're going to just keep growing this tree like this, and then you're going to split it again. This one might have 2 different children like that, and so on. So the big question here is going to be, again, how do we pick which variable and what threshold to use? And this is not at all obvious, I think, but we'll try to work our way up there. So yeah, let me underline that, because how are we going to choose it? And let's just look at a 1D example, and maybe it'll become clear how, well, yeah, we'll use a 1D example and hopefully to build some intuition. So the 1D example that we're going to do is just something like this. And imagine we had maybe some minus points over here, and we had some plus points over here. Something like this. And okay, then we have just we have to split it. So like the question is, how do we split it? Where is the sort of intuitively right place to split it? Well, let's see a few different candidate thresholds and see how it looks. So we could try splitting it over here, where everything to the left is going to be classified as -1 and everything to the right is going to be classified as +1. This would be great for things on the left, because anything on the left of this is clearly going to be a minus. So it seems like it would be very correct on things to the left, but it wouldn't be so correct on things to the right. So maybe this isn't the best type of split we could do. Whereas meanwhile, this would be okay in terms of predicting things on the right. It seems like things on the right maybe would be classified as +1, but things on the left still would have a lot of error. And meanwhile, in the middle is probably like the best sort of thing to do, where things on the right would be classified as +1 and things on the left would be classified as -1. Again, just sort of they take the majority of whatever is in that cell. And yeah, so intuitively, this is kind of the best. And why is it? It's because it makes it so that both the left and the right-hand side are both as pure as possible. Yeah, so like the intuition is going to be the following. We're going to choose splits. Like this is just saying that we already have some sort of dimension. We already know which coordinate we want to split on. But if we just want to pick a threshold, we want to pick a split which makes leaves pure. So that's what we're looking for. And by pure, this is sort of an informal term, but we ideally would like to have most of the leaves being kind of all one class if we can. Homogeneous, pure, I'll use these terms interchangeably. So you can see here that this is kind of pure, but what does it actually mean? Let's try to formalize this. So what we're going to do in order to formalize what our goal is for each of these children, how do we pick one split over another? Well, we're going to define some sort of loss function for a leaf. And the idea is that a leaf, which is going to contain a subset of points, which are sort of classified into there, then we essentially want those to be as close to just being able to predict, we want the majority of them to be all one class. So the intuition is that we want something which is small for pure nodes, but large for mixed ones. And yeah, so we want some sort of function which is going to be, if you have, say, if it's all one class, it may be 0, but if it's like 50-50, then it'll be larger. And So let's see if we can define what the cost of a split is based on, suppose we have this loss function. We'll pick some specific choices for the loss functions. But let's say the best split that we can possibly have, where to pick this threshold, will be something like the following. We'll pick argmin for t of the following. So this is the loss function L. So let me just describe what I'm talking about here, this notation. So this essentially says that we're trying to pick a split. Sorry, let me write this here. All right, so what this says is essentially we're trying to pick a split such that we're going to split the points into two sets. So those with the value of this feature, xi, remember for now we're just looking at a single feature, that one feature being less than or equal to the threshold, and that'll be one set. And so this is this notation here defines the set of all elements with the feature less than t. And sorry, typo here. And over here we have the complement of the set, everything which has that feature being greater than t. So we're splitting it into two sets, and what we're going to do is we're going to compute this. This is kind of like the loss or the cost of the left. So to draw it back to this picture, it's kind of the cost that we accumulate by taking these elements. And here, this is going to be the cost of the right. Now, yeah, so this is essentially how we're going to pick the threshold t star. We're going to pick it in a way such that we minimize the sum of the cost of the left node, where this is some loss function we're going to define, and plus the sum plus the cost of the right. Now, I think this is fairly intuitive. You're basically going to try to pick the split which minimizes some costs. I'll note that this is only looking at the binary tree setting, where you split into just two halves, where you pick a threshold and it's less than or greater than. But you could also imagine, say, a ternary tree where maybe there's 3 children and maybe split into 3 parts. This is something you could do also, but these extensions we're not going to really look at today. But that would just be the sum of all 3 of those parts here. But since we're just going to use binary trees, it's going to just be cost of left versus plus cost of right. Yeah, so it's easy to, that's the sort of way that we're going to pick this. And how are you going to choose the value of t? Which t do you search for? Well, I'll point out that there is less than or equal to n values for t. And the reason for that is because there's only going to be n points in where n is the number of points in our training data set. Well, there's never any reason to try an n or a t which doesn't correspond to a point in our training, which is not in our training set, because yeah, those are the only ones which can change the sum. Anything between 2 of these values will not change anything. I'll note also that there is like fewer for categorical random variables or categorical features. And what do I mean by that? This is the case where we were looking at where it's just some number that you're trying to threshold t on, but maybe xi doesn't take real numbered values. Maybe it's a feature which is, say, 0, 1, 2. For example, I think we use at least one categorical thing. For example, cloudy. This is just a single thing, and it's going to split on whether it's cloudy or not cloudy. So that's a categorical feature, and you don't really have to try multiple thresholds. You just see what type of value it would give you if you split. So good. If it's a continuous number, if it's a real numbered value, or it takes multiple values, then there's more things you might have to try. But if it's only say a categorical feature, then it's very easy to try it without having to test out many different options for the split. Cool. So that essentially tells us the goal when we're trying to pick how to split. The question is, how do you choose these loss functions? Like what is the right type of loss function? And like I said, we're going to want a function which is small for these pure nodes, ones which contain basically all of the things having the same label, but large for mixed nodes, which maybe have half and half. And so there's a few natural example loss functions. So let me tell you a few of them. So let's recall what is going to take in. So a loss function is going to take in a set S, where S is equal to a set of points xi, yi. And yeah, it's going to take in a set of points like this. And it basically has to predict, choose some sort of value, which is based on the elements in the set. And we're going to set up a bit of notation. So p hat c. This is going to be equal to the fraction of S with label C, which is equal also to 1 over size of S times summation of indicator function that yi equals c, where there's the sum over basically points in that leaf. Basically the points that I and S, I guess, is one way of saying it. So, okay, this is a fancy way of saying it. It's just, you just take the empirical, the fraction of points that have that label. It's very simple. For example, if you have, say, a set S where the labels are 0, 0, 0, 0, and 1, 1, then in this case, p hat of 0 will equal to 2/3 because, yep, and p of 1 hat will equal to 1/3. So those are what these fractions here are. And another piece of notation we're going to set up is y hat, which is kind of the prediction. It's the, given this set, which would you predict as a label if you had to predict a label of a new thing? And so this is arg max over c, p hat c. So this is kind of like the majority vote. If your set were these 6 elements and you had to predict a new label, well, the biggest one is going to be 0, so we would have that y hat equals 0. It's the most common label. Good. So this is all the notation we need. These are some concepts which are going to be useful here. And let's talk about some very, very common loss functions that we might use here. So the most common one is the misclassification error. This is kind of the simplest one, maybe not the most commonly used one. And the misclassification error is going to be, I mean, the name is pretty suggestive, but the idea behind it is it's going to be you pay a lot if the leaf would misclassify a lot. So for example, L of S is going to be equal to 1 minus p hat y hat. So yeah, that tells you, this might be a bit hard to interpret, but let's try to look at a few extreme cases. So what if the entire set was zeros? If the entire set was zeros, then p hat 0 would be 1, and y hat would be, p hat 0 would be 1, and y hat would be 0. So therefore, it would be 1 minus 1 and would have 0 loss. So yeah, sorry, let me maybe do that again. So let's just do this simple example. If, say, all zeros, then p hat of 0 equals 1 implies that L of S is equal to 1 minus 1 equals 0. So that's nice because, like we said, if we wanted such that if the set is very predictable for a new label, then we'd be able to get a low loss. So what if it's 50-50? Well, in this case, p hat 0 equals p hat 1, which is equal to 1/2. And so that implies, just plugging in here, L of S would be equal to 1 minus 1/2 equals 1/2. So that's good because you can see when it's like mixed, when it's 50-50, then in fact it's going to be a larger number than it was before. So let's try to plot actually what the misclassification error is going to look like. And let's put this on a plot with some of the other ones that we're going to use as well. So it should look something like this. Let's put it right here. Right here. And we have like the x-axis here is going to be the fraction of ones, just to pick something. So let's say p hat 1 ranges from 0 to 1. And the loss function, which here is a misclassification error, that's also, the value is going to range from like say 0 to 0.5. And the misclassification error, let's color code this red as what it looks like. That's going to be very easy to plot. Let me draw one more point here actually. So right here in the middle, this is going to be say 0.5. So here, what this misclassification error function looks like is roughly the following. Like this. Essentially starts at 0, goes up to 0.5 when it's at 0.5, and then it goes down to 0 again at 1. So this matches the sort of rules that we thought intuitively are good for a loss function. It should be small for pure nodes, where it's all either 0s or 1s, and should be large for mixed. And that's exactly what we have here. Good. This is not always great in practice for various reasons, one of which includes the fact that it's like non-differentiable. It's not as nice as some other loss functions. Some other loss functions which I'm going to mention are, for example, entropy. This is another thing that we might want to minimize. And this equals minus summation. Let me just write it here, and then I'll explain it. So it's a little bit hard if this is the first time you've seen it. So yeah, it's again, yeah, it might not be, if you've never seen it before, you might be wondering where the heck is this coming from. Well, it's going to be, you sum over all the classes, p hat c times log of p hat, and then you take the negative of this. This kind of tells you how random a distribution looks. So in other words, if it is if you have a distribution which has a lot of, if it's very spread out over all the different elements, all the different classes, then it's going to be the highest possible value. But if it's, say, if the distribution is not random at all and it's all just concentrated on one point, then it's going to be zero entropy. So yeah, another way of thinking of entropy is kind of how surprising this set is if you just picked a random element from it. Yeah, so of course we would want this set to be as non-surprising as possible because we're trying to get homogeneous nodes, homogeneous leaves. So yeah, you can verify for yourself, but I'll just tell you that indeed this has the properties we want as well. And let me just draw it for the case where we have c equals 2 classes. So recall we're talking about just when we have 0s and 1s for all these examples, but you could easily extend them also to the case where you're summing over multiple different classes. Maybe it could be 0, 1, 2, 3, 4. But we're just going to talk about binary classification. But what does this look like? If you use the entropy, well, the entropy looks kind of like this, maybe. Yeah, it might not be obvious just looking at this, but it looks kind of like this, which is a nice function for our purposes. Another function which is commonly used for this purpose in practice is what's known as the, I don't know, I've heard it pronounced as the Gini versus the Gini index. And this looks kind of similar in the sense that it's going to be as follows. This is going to be equal to, we have, what is it? We have L of S is equal to summation over classes. And it's going to be the following quantity, p hat c times 1 minus p hat c. And again, this might at least look a little bit nicer than this because we don't at least have any logs in there, which are kind of tricky sometimes. But this is nicer. This might be more convenient to deal with, and it might look also familiar because each of these terms right here is the variance of a Bernoulli random variable with parameter PC. So the idea here is kind of trying to minimize, if we're minimizing this loss function, then we're minimizing the sum of variances over the different classes. And intuitively, again, that's what we're trying to do. We're just trying to make sure each set is predictable as possible. So we'd ideally want something which is low variance. And you can verify for yourself, like this one's a bit more obvious than this, but if you say put p hat c equals 0 or p hat c equals 1, then this will just become 0. But when you set them that they're all equal to each other, then it's going to be larger. So the picture here looks something like this. You can see once again, it has the same property that we want, that it's small in the extremes, but big in the middle. Cool. So those are essentially the different types of loss functions which you would consider. Now, I'm just going to make one brief comment here about regression. Like I said, we're not really going to talk about regression, but if you wanted to do regression in terms of, like I said, these can be used for either classification or regression, we would use a different loss function for a set. So here we were dealing with sort of very discrete things in terms of their labels. We're going to have things being labeled one way or the other. But instead, the way we would do it for would calculate how good a split is by the following, would measure the quality in the following way. We would essentially compute the following. So the idea here is that the loss function for a set S, if you just had a bunch of xi, yi pairs, in this case, the ideal that you could do is basically picking whatever parameter, which would be the best predictor that would minimize their least squared error. And in fact, it's not hard to see actually that if you try to pick the p which minimizes this, that's just going to be equal to the mean of the set. So here is the loss function that you would have. Minus y bar squared. And so this is the mean of yi's in S. Yeah, so that is kind of the way you would do this. You would modify this sort of splitting value for regression if you were to do regression. You just use a different loss function, which similarly tries to measure how pure a set is in some sense. Okay, so this is the main, I guess, part of the lecture where we talk about the different ways to possibly split. How do we see whether a split is good or not? And that's just based on picking a threshold. All right, so that tells how to choose that. So all of this was focusing on how to check and how to value a threshold, but also we didn't try how to choose which dimension or which variable. So which variable to split on. And this is just essentially trying them all because there's only d of them. And so it's not that bad to just try them all in cases where the dimensionality is not too crazy. So let me just sort of write in summary what the way of picking a dimension and picking a dimension of the feature vector and a threshold with which to split on. Is the following way. It's essentially just the same thing that we had before. But let me just write this and interpret it just to sort of cap off this section on how we pick things. Right. So essentially, this is how you pick a dimension as well as a threshold, like this way. You essentially just search over all possible values of j and t in a sort of greedy way. You pick it so that essentially, if you performed the split on dimension j with threshold t, then it would minimize the sum of the losses on both things. So yeah, essentially, let me try to write this in words. Pick dimension and threshold to minimize the loss after the split. And when I say the split using this dimension and this threshold of the feature vector. Cool. So hopefully that kind of intuitively tells you, and more than intuitively tells you, kind of tells you the details on how you might pick a dimension and a threshold on which to split. So let's try to do a numerical example, and then maybe we'll just talk about a few extensions and then call it a day. So let's just do an example with doing these computations on how to split. So let's do a thing here where we're going to do a smoking and cancer example. So let's say one feature we have is someone's age, another is that we have whether they smoke or not, and then the label will be whether they have cancer or not. And so let's see, age, I made some data set, we'll just plug these in. 55. Yeah, right here. And let's just say no, yes, no, yes, yes, no, yes, yes. And whether they have cancer or not, we'll put it over here. Now, the idea here is at this point, we're going to try to make a classifier based on their age and whether they smoke or not, whether they have cancer. It's a very, very simple example, probably unrealistic, but nonetheless, the question is, if we were building a decision tree, then what would we do here and what would we split on in the first index? So what initially would just have some sort of a big node, which would have, there'd just be one node, which just has all the data, and it would be split 50-50 between 0 and 1, so it wouldn't be a great predictor for every point in here. It would only get 50% accuracy if it had to predict. But so the question is, how should we split it? Let's do the calculations. So we're going to use as our loss function, we're going to use the Gini index. And recall the definition of this. We sum over the possible classes C, p hat C times 1 minus p hat C, where this is kind of the fraction of points which fall into that leaf, which are classified with C. So let's compare. So the question is whether we should split on smokes or whether we should split on age, and how we should split. If we split on age, then where we should split on age. So let's start with smokes because it's a little easier. The reason it's easier is because we don't really have to pick a threshold at all, in the sense that we just pick things which are yes, and we pick things which are no. So let's see the ones which are no. That corresponds to this, 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 this. So these four. So we can see of these four, we have that p hat of 0 is going to be 3/4 because 3 of them are 0. So let's say that our vector of p hats is going to be within the no bucket, that is the ones which have no. So those ones are going to have 3/4, and then the p1 will be 1/4. So let me write this. I'm just writing this notation for p hat 0 and p hat 1. So we're going to have no's are going to be 3/4, 1/4, and the yes bucket is going to be, let's just look at those. Yes, 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 yes. So here we can see that 1/3 of them are 0s and 2/3 of them are 1s. So we have 2/3, 1/3. And so these are our sort of p hat vectors. And now let's just calculate the Gini index. for the nose, we're going to have here being, what we do is, we just calculate it. It's going to be, first for p hat 0, it's going to be 3 over 4 times 1 over 4, and then plus 1 over 4 times 3 over 4. So this should be like 3 over 8. And here, similarly, we just do the same thing. 2/3 times 1/3 plus 1/3 times 2/3 equals 4/9. So the total cost of performing the split on smokes would be 3 over 8 plus 4 over 7, or 4 over 9 rather, and this is approximately equal to 0.82. Okay, so that tells us how much cost we would have if we split on smokes with the only value that we can. Okay, let's see the other end. So let's see what happens if we split on age. Well, okay, splitting on age is a bit trickier because we actually have to choose a threshold as well. But I'm going to cheat and just eyeball this. You can tell that maybe this is perhaps the best place to split on age because everything above is going to be 0s and everything below is going to be 1s except for one of them. So yeah, I'm going to cheat and say our threshold could be, say, split on less than or equal to 35, let's say. And then there, within this set, we have that the p hat 0 is going to be 1, and p hat 1 is going to be 0. And below here, greater than 35, we have that p hat 0 is going to be 1 over 6, and then p hat 1 is going to be 5 over 6. So we can easily do these calculations again. So here we have 1 times 0 times 0 plus 0 times 1 is equal to 0. And here we have, I guess I'll just simplify the calculation, say it's 2 times 1 over 6 times 5 over 6. And yeah, this is equal to, 5 over 18, which I don't know what that is, but it's less than 1/3, so it's less than or equal to 0.33. And in particular, it's much less than 0.82. So you can see that the split that caused the smallest loss function in terms of how good the split was is going to be this one, where we split on age. And in particular, we split right about here. And you can see it kind of makes sense because everything in one half is going to be homogeneous and everything in the other half is going to be homogeneous. We made these very uniform in these two bins that we split into the two leaves we split into. Good. So that's basically how you choose the how you do the algorithm. You start with a node, you split it based on choosing you choose a dimension and a threshold, and then you split it somehow with that, and then you repeat and you repeat and repeat, so on. That's great. We told how the algorithm runs, but we haven't told how to stop. Of course, you're going to need to know how to stop at some point. And there's a few different ways you can do it. Well, one way to do it is based on depth. So maybe you say if you get down to a tree, which is say at least like at most 10 levels, once you reach 10 levels, maybe that's deep enough and then you stop. Another way is maybe for running time. You run it for like maybe several minutes, and then after you do that, then maybe you don't have any more time, so you just run it for a while and then call it quits. Another thing is when you have sparse leaves. What do I mean by sparse leaves? Suppose there's a node. Okay, initially when you start, you're going to have a data set which is hopefully huge, maybe hundreds or thousands of points in your leaf root node. But then when you split, it's going to split it into fewer nodes in each of them, and then each of the children is going to have fewer nodes, and so on. And maybe you get down to a place where there's still some uncertainty, like maybe you still have 50-50, but this maybe only has 5 points or something. Well, if there's only 5 points in the leaf, then it's maybe kind of hard to split further in there because you're not really getting much useful information. So this is what I mean by sparse leaves. If you get down to a node where there's only very few points, then maybe that's a good place to stop. So that's what I mean by sparse leaves. Yeah, another time to stop is when leaves are homogeneous. For example, like in this case, when you split here, you can't split these zeros any further. There's only zeros in this leaf here. So there's no way you would split these folks less than 35 into two parts anymore, just because they're all the same anyway. And a kind of another sort of way, which is a little bit more general than that, is by when the improvement from splitting is minor. So like small improvements. And by that I mean that we have, say, delta, which is equal to, say, we have L of S first, so this is before a split. And then after a split, maybe we have a split into two halves, SL plus L of SR. So all I'm trying to say here is if this value here, this delta, where this is the loss before the split and this is the loss after the split, if this is a small number, then maybe we're only getting a minor or marginal improvement in our prediction. So therefore, we can stop if this gets too small. So those are some ways to choose when to stop doing our decision tree. Okay, the last thing I'll mention is sometimes this early stopping can be harmful in the sense that maybe you should have kept going, even if it seems like you're getting small improvements, maybe there'd be a bigger improvement later. So this early stopping can sometimes be a bad thing. So another thing we do is what's known as pruning. And pruning, essentially, I'm not going to get into details about it, but essentially it's the following, where you grow the tree fully. By that I mean you don't give up if things are, say, only making small improvements in case they could make bigger improvements later. You don't stop based on running time. Maybe you only stop when you have homogeneous leaves or very sparse leaves with only a few things. But yeah, you just basically let it keep going without stopping early for any reason. And then you kind of regularize over subtrees. And what do I mean by that? I mean, you essentially are going to do the same type of thing that we've done many times before, where, yeah, what's the way to say this? Again, I don't want to get too much into details about this, but the way you might do it is, suppose there's some sort of tree you have, which is a big tree, something like this, and it gets some sort of error, in the sense that if you sum up how much error is contained in each of these leaves in the tree, so here, 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 and here. So yeah, maybe let me write this here. Like you have some sort of sum over error in leaf in leaf V, where the summing over, say, all leaves V. So that's one thing. And then plus alpha times number of leaves, where this alpha here is a hyperparameter. And the goal is to minimize this. So okay, this is a lot of stuff, but let's try to parse sort of what I mean. So this is what we'd like to minimize. So there's kind of two things we'd like to minimize. Of course, we'd like to minimize, one, the sum of the errors in each of these leaves. And then the other thing, we'd like to minimize also the number of leaves. So what do I mean by minimize the number of leaves? Well, the idea is we can prune this tree. So one way of pruning is kind of just sucking some of these up back into their root nodes. So this is one tree that we could prefer. That's sort of the final tree that we would have learned. But another subtree is something that looks like this, where you can see this has just been contracted here. Another one that we could have considered is when we contract the right thing again. And the other thing is when we contract it all just into one node. So you can see these are 4 different subtrees of this sort of full tree. And each of these will have a different value in terms of their error in the leaves. And the idea is that the fully grown tree, basically what we were trying to optimize the whole time was trying to minimize the sum of the errors. So this one's going to have the best value for the first term. But you can see also that it has the most leaves, so it's going to pay a lot in this term. So in short, the idea here with this loss function is that it's going to, it's going to somehow simultaneously try to penalize it for having a lot of error, but also penalize it for having a lot of leaves. So this one would get hurt a lot by the number of, based on the fact that it has a number of leaves, which is a lot. Whereas things more on the right-hand side would be, that would not pay a lot in the second term, but maybe it would pay more in the first term. So you can see if like the two extreme cases are if alpha equals 0, then it would pick this case every time. Because, like I said, this is essentially what we're trying to optimize for when we're doing this decision tree building. And meanwhile, on the other hand, if alpha equals infinity, that's just saying make sure no matter what the number of leaves is minimized, and that would correspond to this. But there can be some trade-off where you might prefer one of these other trees based on the size, and yeah, you'd pick this hyperparameter using cross-validation or validation set as usual. Cool, but that's all the detail we're going to get into. You can look up more if you're interested in how we do pruning. The very last thing I'll mention is something called a decision stump. A decision stump is the following, which is basically just a very simple decision tree. It's just like, it splits like this. It just takes one feature and it thresholds that one feature with one value, and then it makes a decision. So yeah, it's kind of just a very silly, simple looking tree. So yeah, that's all there is. It's like, well, why would we care about this? Well, one reason we'd care about this is it's fast. You know, it's very easy to make one of these. You just sort of pick one feature and one threshold, and then you're good. Very fast to do inference as well. You just look at one feature and see if it's cross some threshold or not. So that's great. The downsides are that it is obviously perhaps just making a prediction based on one feature, not very good. Nonetheless, it's still going to be useful in the next lectures when we're going to talk about things like boosting and bagging, where kind of, even though the fact that these aren't very good, it's a very, very simple classifier, it's still going to get you some advantage over random guessing, like maybe 50-50, it'll give you a little bit of advantage, and we're going to see how maybe given a bunch of things which are not very good, we can put them together to make one thing which is better. So yeah, that's it for today's lecture on decision trees. Hopefully you see that they're kind of an intuitive idea, and the main sort of tricky part is figuring out how to build one in terms of choosing how to split. But yeah, if you just do it with the right functions, then it shouldn't be too bad. That's decision trees.